late, but was trying to, I left everything ready on the computer, but the computer restarted. So. Coming back to our class of Monday, I would like to present to you some aspects of the Metropolis-Hastings algorithm, like the implementation and also the some practical aspects, and especially about this. Oops, I'm sorry. About this proposal distribution Q and how it affects the solution. So just a reminder that we are talking about the Metropolis-Hastings algorithm, which is an implementation of a Markov chain Monte Carlo method. So it's a Monte Carlo method implemented to generate Markov chains. And having the values of our vector of parameters at some state t minus 1. So t does, it looks like time, but it is not time. This is a state of the Markov chain. And then we generate candidates for the Markov chain, which they are denoted here as P star, with this proposal distribution Q. Okay? So Q is how we move in the Markov chain. And then we compute this acceptance factor. It's called also the Metropolis-Hastings ratio, which is basically a ratio of the posteriors at the candidate point and at the point at the previous state, multiplied by the proposal distributions of the ratio of the proposal distributions for moving from P star to PT minus 1, and PT minus 1 moving to P star. And then we generate a random value U that is uniformly distributed between 0 and 1. So U has a uniform distribution in this interval. And if U is smaller than alpha, then we accept the candidate point. Otherwise, we reject the candidate point, and we make the state of the Markov chain. We make the vector at the state t equal to the vector of the state t minus 1. Okay? And then we repeat this until we get sufficiently happy that, and we hope that we are going to get a Markov chain that will represent an equilibrium posterior distribution. Okay? So we saw some this is not working, but okay. So we saw some practical aspects about the priors, the likelihood, and then we came to this example, okay? And this is what I would like to show you. First, the first Matlab code is about this example, where we have a semi-infinite medium. So this is like a plate, which is infinite in this direction, also infinite in the direction perpendicular to the board. And it's semi-infinite here, okay? And this plate is initial at temperature T0. And at time T equals 0, for times larger than 0, this surface is maintained at the 0 at temperature T equals 0. So this is the solution of the problem, where we have two parameters, T0 and alpha, okay? And then we present to you the results for a case involving concrete, where alpha, the thermal diffusivity, is 4.9 times 10 to minus 7 meters squared per second, and T0 is 50 centigrades. And then we examined the sensitivity coefficients, and we saw that the sensitivity coefficients were linearly independent, and the conditions were good for the estimation of the two parameters. So in the first case, related to this example, I'd like to show you a case where both parameters can be estimated, okay? Because the sensitivity coefficients are linearly independent. And in a second example, I'm going to show you a case where the parameters, they are completely correlated, okay? And so how we deal with a case like this, okay? So we have this Matlab code, and, which I'm going to pass to here, okay? And where, oops, it's so small. Let me try to increase the size of this. Of the font. Oops. Try to increase the size of the font here. View. No, publish. Editor. New open comment event, breakpoints from time. Algum de vocês sabe como que aumenta o publish? Não.
Viu?
Não. É? Aí aumenta tudo? A resolução?
Diminui a resolução.
Diminui?
É. 800 por 600, é isso. Mas é de lá, né? Você está diminuindo a sua. Aqui, ó, clica aqui em cima.
Ok.
Vai aumentar o tamanho da sua... Aplicou já?
Já.
Acho que você fez isso na tua tela. Acho que tem que
Não, mas não
aqui.
tem problema.
Aí, agora muda lá.
Muda agora aí.
Aqui?
Isso.
A 1024?
Isso.
Mas aí o problema é que...
Não, depois você volta.
Você...
Bom,
Isso, joga a janela pra lá depois. Não sei se vai. Aí.
ok.
Depois você fecha o slide, abre de novo e vai voltar ao normal.
Tá bom. Ok, obrigado. Okay, so let's take a look at this Matlab code, where here we have these are the exact values that are used to generate simulated measurements in a final time of 250 seconds, and the measurement position is 10 millimeters below the surface. So this is the exact temperature, the exact solution. This is the computation of the sensitivity coefficients, which are analytical, and then we have a plot here of the sensitivity coefficients and of the exact temperatures, okay? Okay, now let's go for the simulated measurements. We have here a standard deviation of 1 degree centigrade. So I generated simulated measurements by adding a random vector with a Gaussian distribution and zero mean and unitary standard deviation to multiplied by the standard deviation of the measurements, okay, to the exact temperature. And then there is a plot of the exact and measured temperatures. And then we started the Markov chain, okay? So these are the minimum and maximum values for both parameters. And in this case, as you remember from the other class, I have like uniform distributions within these intervals. Okay. And in this case, I chose to start the Markov chains in the middle of these intervals. Okay? I could have started at any other point inside the interval. Why inside the interval? Because from the prior, I know that the probability of having the parameters outside these intervals, it's 0. Okay, so we have the first state of the Markov chain, and with this first state, I compute the estimated temperature. I'm computing the estimated temperature also from the exact solution so in this case, actually, I'm committing an inverse crime. But I'm not worried about this. I'm worried about presenting to you the effects of the Markov chains, okay? Of the different parameters over the Markov chains. Then I compute the likelihood, okay? Since I have the temperatures, the estimated temperatures, and I have the measurements, I can compute the likelihood. Actually, I'm only computing here the exponent of the likelihood, okay? And it also misses a minus sign here. So what I mean is that oops. Vai voltar? Ok, obrigado. Okay, so what I mean is that I have Gaussian likelihood, and something going on. Okay, so I have this Gaussian likelihood, okay, but what I'm computing there, it's only what is inside the curly brackets here, okay? So it's only the exponent. And I'm not considering here the minus sign, okay? You'll see, I could have put the minus sign there. No, but that's the way I coded a long time ago. Okay, and then we have, so this is the whatever is inside the exponent of the likelihood. In this case, since we have a Gaussian likelihood and we have uniform priors, the posterior is equal to the likelihood, okay? Because we have uniform priors. Then I save the first state of the Markov chains, okay? I save that this T0, the alpha, and also the posterior. And then I start the Metropolis-Hastings algorithm, which I'm going to run for 20,000 states. And I'm using a burn-in period of 10,000 states. So I'm going to neglect the first 10,000 states. Okay? And these are the size of the maximum size of the variation that we are going to have in the proposal density. Okay, so this is the maximum step size that I'm going to take when I move from one state of the Markov chain to the next state. In other words, this is the maximum size that I may take to generate the new candidates, okay, for the Markov chain. Okay, so we have a loop to generate states for all the 20,000, to generate 20,000 states. Okay. How do I generate these new candidates? I generate with a uniform distribution. Okay. So rund is how the MATLAB generates a uniform number between 0 and 1. Since we have here 1 minus 2 multiplied by this random number, this can vary from -1 to +1, okay? And any number in this interval is going to be multiplied by this step size of the proposal, okay? Which is WT0 and W alpha. Okay? And I generate the same way for them. Okay? So I generate the candidates, and I have to decide if I accept or not these candidates. And since I'm using uniform distributions, I know that outside this interval, the probability is 0. Okay? So I even don't have to make the Metropolis-Hastings test if the candidate is outside this interval because the probability is 0. We are not going to accept it. Okay? So then I check the limits, and I'm only going to do the Metropolis-Hastings test if the candidates are inside the lower and upper bounds for both parameters, okay? For both parameters, for T0 and for alpha. Okay, so if it is inside this interval, I compute the estimated temperature with the candidates, okay? Because I have to compute the likelihood. So I need the estimated temperatures, I need the estimated response of your system, of your dependent variable that you are measuring, to be able to compute the likelihood. Okay? So I compute the new likelihood, also without the minus sign. Okay? And the posterior is equal to the likelihood because I'm only considering candidates inside the interval where the probability is different from 0. Outside this interval, the probability is 0. Okay. Now I'm going to do the Metropolis-Hastings test. So what we have here is something a little bit different from what we have in the transparency. Because in the transparency, see, I make the Metropolis-Hastings test. Sorry. Okay, like this, okay? So we have the posterior, okay? Which is proportional to the exponential, okay, of minus 1/2 y minus t transpose w minus 1 y minus t, okay? And so when we have to do this test, alpha is equal to the exponential of, it's the minimum. Of 1 and the exponential of minus 1/2 y minus t at the candidate point, transpose w minus 1 y minus t at the candidate point, divided by the exponential of minus 1/2 y minus t at the previous, I'm calling it there, t minus 1. W minus 1, y minus t, p t minus 1. Okay? So this is the exponential, close here, and I have this. Okay? So the minus sign that I did not use there, okay? So it's a ratio of exponentials. So this is going to be this guy minus this one here, okay? So since I'm only computing positive quantities, I'm going to put a minus sign here and a plus sign here when I divide the two exponentials, okay? And besides that, to compute alpha like this works very nicely if this exponential, the ratio of this exponential is a negative exponential because then it has a small value. But if this is like if you are moving in a direction that the posterior decreases, okay, you might have a positive value and a positive exponential that will blow up very fast and very easily. And that's the difficulty. It's a numerical difficulty. It's not actually anything related to mathematics. It's purely numerical. No? So instead of doing this, I'm going to take the logarithm alpha, and then I work here, okay, with the by subtracting this quantity from this, subtracting this quantity from this quantity here. Okay, so I take the logarithm. This is only for the sake of the implementation of the method, because otherwise you may end up getting some not a numbers. Okay, so instead of and another point, if this is larger than 1, you always accept it, right? Okay? So if this is larger than 1, no problem, you accept it. Because alpha, it's between 0, when you compare u less than alpha, okay, u is always between, this is a uniform distribution between 0 and 1, okay? So if the posterior is larger, you accept it, okay? But even if the posterior is smaller, you might accept with this probability u. Then the point is that I don't have to compute this minimum here, okay? Okay, I only need to, because u is always between 0 and 1, okay? So I can do directly the test without taking this minimum, because whenever this is larger, it's going to be accepted anyways. Okay? So we don't need to waste time computing the minimum there. Okay? Computational time. Then I take the logarithm, and then the logarithm, if the logarithm is smaller, then minus posterior plus minus the new posterior plus the old posterior. So that's what I meant when I didn't have here the minus sign, okay? Because I'm putting the minus sign here, okay? So if this is true, I accept the candidates. I also save the likelihood and the posterior, okay? I increase this counter, and this counter is the number of accepted states. And then I save all those guys here, okay? I save all those guys. And of course, if this is not true, I'm going to save whatever is the old values, whatever are the old values, okay? So I only update the old values if the Metropolis-Hastings test is true, okay? And in this way, I generate the Markov chain. And here I'm dividing everything by this exact value, okay? T0 est and is this vector of with each point of the Markov chain, at each state of the Markov chain. And same thing for alpha. And I'm dividing by the exact value, so I have everything 1, okay? You don't have to do this. This is only to make nice graphs. Then I present a graph with the states of the Markov chain for T0 and also for alpha. And I plot the logarithm of the minus likelihood, okay? And the number of accepted states. And after I do this, okay, I remove those initial states that are related to the burning period, okay? So I only keep here, okay, the states between the burning period and the final state, okay? And then for those guys, I compute the mean, I compute the standard deviations, and I also compute the quantiles, okay? So we cannot say in advance that this is a Gaussian distribution, but you can compute the quantiles because you have samples that represent that posterior distribution. Okay? And this is also plotted. Okay? So let's run this thing to see how it goes, and then we play a little bit with the parameters. What is okay? Okay. So okay. Just one moment. We are running 20,000 states. And although this is very fast, this is not a fast computer. Okay, just 1 second. So we have a Gaussian likelihood. We have a posterior that is uniform. So what we actually expect is a Gaussian posterior. Okay. It's almost there. Okay. Okay. All right, so this is the histogram of the samples after we drop the burning states. And we can see that we get a nice result, okay? This is the credibility interval, and 99% credibility interval. And the exact value is here, but we still get some, the largest probabilities is somewhere very close to 1, okay? And then this is for alpha, and this is for T0. Which is a nicer result. And this is for, oops, I'm sorry. These are the states after we reach equilibrium. Okay, so 1 and 1 is somewhere around here. So this actually represents our posterior distribution. Oops. These are the number of accepted states. From the 20,000 states, we accept 12,000, which is a little bit large, because people say that we should be around 30% of acceptance to have some statistical representation of our posterior distribution. Okay. So it's a little bit large, but that's okay. And then here we have the oops, I'm sorry. I wanted to show you guys something. I probably skipped here. Okay, that's what I wanted to show you. This is a picture of the likelihood, okay? So this figure, we have the variation of the likelihood, actually the logarithm of minus likelihood. And we can see that after 10,000 states, the likelihood almost does not vary. So this gives us some confidence that the Markov chains that we are generating, they represent an equilibrium Markov chain. So then we have the alpha. This is the Markov chain for alpha. So we start from 10, you see, a value 10 times larger than the actual parameter. And it goes down, and eventually it reaches here, like a value around 1. And if we make a zoom here, we can see that over there, it's not constant. It should not be constant. It should not be constant because we actually want to represent the posterior distribution in terms of its samples. So if this is constant, this is a bad representation of your posterior because you have one single parameter, or have one single value to represent a distribution. We actually want there are a lot of values to be samples, to be representative samples of your posterior distribution. Because since we cannot compute the posterior, we are making statistics, we are computing the statistics of the posterior in terms of the statistics of the samples. Okay, okay, so this is for alpha, and this is the value for T0. Okay, so we see that we start from here, from 1.05, but we go up. Okay, so this is probably the upper limit. So above it, it's never accepted, no? But then it comes down again, and we have this Markov chain, which does not look very nice, because it looks like a kind of periodic here, right? So like a low frequency period, right? And something like this looks much nicer, okay? Because this is actually only the random character of the posterior. Okay. And only as a reference, here we have the exact, what would be the exact measurements and the simulated measurements. Okay. So this is actually a kind of, really a kind of noisy. Okay. Okay, so now let's change things a little bit. Let's do the following. Let's increase the let's play a little bit with this step size here. Okay. So instead of having 5 10 to minus 4, okay, let's decrease it. Okay, let's put it here like 5 10 to minus 6. Okay? For both of them. Okay. So now since we are taking a much smaller step, most likely we are going to accept a lot of states. But we are moving in the Markov chain very, 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 very slowly. Okay? So this means to actually have an equilibrium distribution of the states of the Markov chains that hopefully represent the posterior distribution, we would need a lot of states. Okay, many more states. Okay, many more states. And you see, this is actually what is happening here. See, this is for alpha. You see, alpha is still there around 10. T0, it's still there around 1.05. But you accept a lot of states, actually, okay? So actually, here, alpha, it's still not in the range that I plotted here. See how many states we accepted? 18,000. So we increased the number of accepted states. We accept a lot of states. But take a look at the likelihood, okay? So we can clearly see that the likelihood has still not reached some value that can be considered as that we can consider the chain as a representation of our posterior distribution. Okay, and so this is the value of alpha. This is the chain for alpha. You see, it's still going very, very, very slow here, and this is for T0. Okay, so these are bad chains, very bad chains. Okay, these are very bad chains. Okay, now let's increase it a little bit, okay? Let's not do 5 10 to minus 4 that we had before, but 5 10 to minus 5. And let's see what we get. Okay. This is the histogram for alpha. See, it's not 10 anymore, but it's still not 1 as it should be. And look that this is pretty much uniform, and we expected a Gaussian distribution since the posterior is Gaussian, right? We have a Gaussian likelihood and a uniform prior. More or less the same thing for T0. And the number of accepted states, it has increased. See it about 12,000. Take a look at the likelihood, how it is. Okay, it's still decreasing. So we don't have a converged chain, which is actually what we can see here. Okay, and then this is the chain for T0. Okay. Okay. So before we had this 5 10 to minus 4 gave a nice result here. Let's put it here 5 10 to minus 2 to see what happens. Okay. So now we have we are taking a very large maximum step. So what happens now is that since the step is so large, it will be very likely that we don't accept the states, okay? And then the chain will look like this. We'll have like some constant values jumping here and there, okay? Only when we accept it, okay? And at the same time, this is not good because since many values for the states of the Markov chain, they are all equal. Although we have a lot of states, they do not actually represent, they cannot be considered to represent the posterior distribution. And this is what we get, you see? See that we have something here around 1. So it actually dropped to some value around 1. But this is very strange, right? So it's a strange posterior. Same thing here for T0, okay? And you see that whatever was expected to represent the posterior density, there are very few states there, okay? It looks more or less like the first picture that we saw, but there are not many states. And see how the number of accepted states are. We only accepted 40 states out of 20,000. Okay, out of 20,000. So the posterior, it actually drops. Okay, and this is the Markov chain for alpha. So you see that we started sampling, generating candidates up to a point that we somehow accepted a value close to 1, and then we stay there. Okay? So if we make a zoom here, see? Very little states they are actually accepted. Okay. And this can be also seen with the chain for T0. Okay? So when you see a chain like this is bad. A periodic chain is bad, and also a chain like this is bad. Okay? And what I wanted to show you with this example is that even for a very simple case, that the parameters are not correlated, and also that we have a uniform prior, and we are generating the samples with a uniform proposal. If we do not select this proposal appropriately, we get very bad results. Okay. There are some empirical results in the literature, for the choice of this maximum step that you can take in the proposal distribution. Okay, so there are some papers in the literature about this. Okay, something like if you take this 0.1 divided by the square root of the number of parameters, especially when here we did a uniform proposal. I'm going to show you now how we do with a Gaussian proposal. Okay, with a Gaussian proposal. But so you have to play with the values of the parameters a little bit. And another thing is that you can only, this as I said last class, you can only compute the statistics of the samples of the Markov from the Markov chains, that hopefully they represent the posterior after you generate the chains, okay? And this takes long, okay? This can be long. So this is a drawback of this method, okay? This is a drawback of this method, okay. So let's look now when we have a Gaussian proposal, okay? So this is exactly the same code as before, except that I'm generating candidates with a Gaussian proposal, okay? So run the n here, and run the n here, and WT0 and W alpha, I have used the same values as before, but they only for the sake of checking how this works, okay? Now we have a Gaussian proposal, okay? So 100n is a number, it's from a standard Gaussian. 0 mean and unitary standard deviation, and then we multiply by WT0 and W alpha, which correspond respectively to the standard deviations of T0 and of alpha. Okay? You see that the parameters, the priors for the parameters, they are still uniform. So what I'd like to show you here is that the prior represents your knowledge about the parameters before the measurements are taken. Okay? So this comes from your experience, this comes from literature values, this comes from other experiments that you did in your laboratory, or even from your beliefs, that of course they are represented in terms of some statistical distribution. And in the proposal, as we saw, we may have independent moves, where the proposal, the candidates, they are sampled from the prior. We can do this, okay? But here it's not, this is not what I'm doing, okay? I'm generating samples from a random walk with a Gaussian, from a Gaussian distribution, okay? And this actually has nothing to do with the prior, and it doesn't have to do, Okay, so this is completely independent. Okay, and this is the histogram for alpha. This is the histogram for T0. They are both very good. This is the posterior, the samples there that represent the posterior, and the number of accepted states, which is more or less around 50%. The likelihood, okay, the likelihood, and also the chains for alpha. And again, we can see that it's a very nice chain. And actually, in this case, we get a nicer chain for T0 than we had before with the uniform proposal, okay? All right, so now let's take a look at the code for a Gaussian prior, okay? So now I have a Gaussian proposal, and a Gaussian prior. So since I have a Gaussian prior, okay, actually it's a truncated Gaussian. It's a truncated Gaussian, okay? I still have here the minimum and the maximum values of each parameter, okay? But inside these intervals, the distribution is Gaussian, the prior is Gaussian. And so let's say that we start here with a value that is 1.5 times larger than the exact values, that this is the mean. So I'm prescribing a very bad mean, okay? I'm prescribing a very bad mean. But let's assume that I don't have great confidence on this mean value, okay? On this mean value. So I take here maybe a standard deviation for T0 that is 50% of the value, I'm sorry, yeah, it's 50% of this exact value, okay? Of course, I'm here in this example, I know the exact value, but the problem is when you are doing the real experiments that you don't know the real value, okay? So in my prior, I have completely wrong mean, okay, for my prior. But I'm accepting that I don't have great confidence on that mean value, okay? So I'm prescribing a Gaussian prior with a very large standard deviation, okay? Okay, so the difference now is that now we compute the likelihood, okay? But the posterior, we add the likelihood to the prior, okay? And we have a Gaussian prior here, okay? We have a Gaussian prior for T0, a Gaussian prior for alpha, which they are also only represented in terms of that term inside the exponential, okay? And when we generate the candidates, I'm generating the candidates with a Gaussian random walk, and I check the limits, because since I know that the lower and upper bounds for each parameter, if the candidates they are outside this interval, we have 0 probability, okay? And if they are inside that interval, then we compute the likelihood, the new likelihood, and also the new posterior. And now the posterior, we have to add to the likelihood the Gaussian prior, okay? And all the rest is the same. So let's run it and see how it goes. Here, 5 10 to minus 4, the maximum step. Okay, so I'm basically saying that I don't have great confidence in the prior. Okay, but I need to be fair enough with me, right? And see what we get, okay? Very nice result for alpha. Very nice result for T0. The distributions, number of accepted states, which are kind of large, but the posterior, and the Markov chains for alpha and for T0, okay? So, got a very nice result, but I'm using a completely wrong mean for this Gaussian, okay? And but I'm accepting that I don't know, I don't have great confidence on this mean, okay? Now, let's do a totally different thing, okay? Let's also keep the mean completely offset, okay? But let's assume that I'm completely wrong and I have great confidence on this value, okay? Let's assume that we have great confidence on this value, so which is totally wrong, okay? So instead of prescribing a standard deviation of 0.5, let's prescribe here 0.01, okay? And same thing for alpha, okay? So what is the point here, okay? Let's say that I'm getting a value of alpha from the literature, okay? I open the book, I get a value for alpha for the thermal diffusivity, and I say, no, this concrete has this thermal diffusivity, and I have great confidence on this. But actually, it's not, okay? So let's see what will happen, okay? So I'm prescribing a mean value that's completely offset, and I'm saying I have a great confidence on this value, okay? For instance, I am running 30,000 states instead of 20,000. Okay. This is the histogram for alpha. Very nice Gaussian distribution, right? But look where it's centered. It's centered completely offset from the exact value, which should be 1, okay? Same thing for T0. It's not as bad as for alpha. It's not as bad as for alpha, but it's still very bad. And it's not as bad for alpha because the sensitivity coefficient for T0 has a magnitude larger than the sensitivity coefficient for alpha. But this is completely wrong, right? So what I did wrong here? I got some inputs to prescribe my prior, which were wrong, but I accepted those values with great confidence. So what's happening is that we are getting a nice Gaussian distribution. We'll probably see converged sample, converged Markov chains, equilibrium Markov chains, very nice Markov chains. But we have a bias. We have a bias. As we saw before, okay, regularization although regularization is not an issue here since we are only estimating 2 parameters from a lot of measurements, okay? So although regularization is not an issue here, Regularization comes out from the prior. But on the other hand, the prior introduces bias on our inverse problem solution, okay? So we have to put a lot of thoughts on the prior before we specify it because this will have a large influence on our result, okay? And only for the sake of showing you here the posterior, see? The posterior looks nice. The Markov chains, they also look nice, okay? See? The Markov chains look nice. But we have a very bad result, okay? We have a very bad result because we got stuck at some point, some equilibrium distribution which is not exactly the posterior distribution obtained with the parameters with the exact parameters, because the effect of the prior was very strong, okay? The histograms are not actually centered around 1.5 because we had the likelihood working, okay? The likelihood was working, no? Trying to bring the parameters to their exact value, no? Because we wanted to represent appropriately the measured temperatures, okay? To appropriately represent the measured temperatures. So we had the effect of the likelihood, okay? But we also have the prior that is pushing the values towards the means that were specified with a very small standard deviation, okay? With a very small standard deviation. Okay, questions? And of course, if we put it here, even if we put it here like 1 and 1, this would be the best of the worlds, right? The best situation would be one that like we knew the parameters very well, and we are only taking new measurements with those very well known parameters. No, they're known with I know the exact mean with a very small standard deviation. And I'm simply running new experiments, you know, and bringing in this prior information from previous experiments, which actually will result in posteriors that have smaller standard deviations, okay? Smaller uncertainties, since we are reducing the uncertainties with the new measurements that we are taking, okay? And okay. Okay. So this is the histogram for alpha. This is the histogram for T0. Both of them are very nice. This is nice. We accept a lot of states because the uncertainties in the prior, they are so small that you're actually around that region where you have the parameters are most likely, which is prescribed by the prior. This is the posterior, Markov chain for alpha, and Markov chain for T0, okay? Markov chain for T0. So, I mean, like from these examples, we have seen that we have to be very careful, both in prescribing the prior, okay, and also how we select the the proposal distribution. Okay? How we select the proposal distribution. And Gaussian proposals, Gaussian random walks, they are nice. But still remains a question about the standard deviation of this Gaussian move. And you can you should always play a little bit with this standard deviation of the Gaussian proposal. And there are some suggestions in the literature, some empirical suggestions in the literature for selecting this standard deviation, okay? That depend on the number of parameters, and you can also play a little bit with them, okay? And moreover, there are some works in the literature that work with an iterative proposal. So the proposal, it kinds of get adjusted during the generation of the samples of the Markov chains. Okay? And these are very nice works, and the generation of the Markov chains like this, they should also be tested. Okay? And in addition, there are works that there is at least one work with an algorithm that works very nicely that to work with multiple chains. Okay? And then you generate multiple chains and you make inference from those multiple chains. Okay? And Daniel Vatsenig, he even mentioned one of these papers during his talk last week. Okay? So this is something that I'm not discussing here. Okay? So questions? Okay, so let's move on. And okay, so after we saw this example, okay, we discussed a little bit on some practical issues about the representation of the statistics of the Markov chains. Just 1 minute, get stuck there. Okay. So we finished our last class about talking about this output analysis, that after we generate the chain, we can do any statistics that we want, okay? And we also saw that in addition to computing the mean of the samples of the Markov chain, we can also compute the uncertainties associated to these mean values, okay, to the mean values for each parameter. Why? Because first of all, we expect that the mean converges to the expected value of the parameter when the number of states used in the analysis grow. Okay, this is the law of large numbers. And we know that if we had independent samples, I mean, the variance of the mean is going to be the variance of the samples divided by the number of samples. Okay? And this would be the case if we had independent samples. But since we do not have independent samples, as we saw, when we have very small step, okay, for in the proposal. When we propose candidates by taking a very small step, they are very correlated because they look pretty much like the previous ones, okay? And at the same time, when we have a very large step used in the proposal, we get a lot of correlated states that they are all equal, okay? In both cases, we need very long chains, of course, and this is reflected here, okay? This is reflected here because this number tau, which is the integrated autocorrelation time, tau represents the number of states that we need to get an independent sample, okay? To get an independent sample of the chain. So when we saw how to compute tau because we can compute this normalized with this normalized autocovariance function, okay? We can compute which is the covariance of a state at a certain of the values at a state at some state R, the correlation with respect to the size k. So it's the covariance of the value at state R and this at the state R plus k. And this is divided, the normalized autocovariance function, this quantity is divided by the same autocovariance function but with a lag 0, which of course is the covariance, is the variance of the value of the state because this is the covariance of at the state R with covariance at the state R also. Okay, so this is the variance, and it can be shown that tau, okay, the integrated autocorrelation time is given by this expression, and actually we don't have to sum up these quantities to infinity, up to infinity, because you expect that this drops out very fast. This would be nice if this drops very fast, okay? Because rho is equal to 1 for k equals 0, which means that the state is perfectly correlated with itself, okay? But since the Markov chains represent a stochastic process, it should represent a stochastic process, you expect that rho drops to 0, and then it stays oscillating because of the stochastic characteristic of the chain. Okay, this will only be noise. Okay, so we can see this in an example too. Let me try to find here. Let me just 1 second, please. Correlation. Okay. Okay, so a very simple example, okay? I'm generating 100 random numbers from a Gaussian distribution with unitary standard deviation, okay? Zero mean and unitary standard deviation, standard Gaussian, okay? And I compute this exactly that a normalized autocovariance function, okay? The rho. So this is 1, and then it drops to 0, okay? But in the case of a Gaussian distribution, since the samples, they are completely independent, okay? I'm sampling independently from this Gaussian distribution. This should drop to 0 and keeps oscillating like noise, okay? And so this is the function from the Matlab that computes the normalized autocovariance function rho, and you see that's the result that we get. Okay, let me show you. See, this is 1, and then it drops to 0, and it stays oscillating because this is only noise. Okay, and the way that function computes. Okay, so it computes the autocovariance function forward but also backwards. Okay? That's why it's centered at the, we have 100 samples. Okay? We have 100 samples here, so one is centered at 100. Okay? It's centered at 100. So then we can actually, we don't need to, for the computation of tau, we don't need to make that sum up to infinity because we would only be adding noise, okay? We can stop the sum when we get, for example, about, let's say, when rho, the autocovariance function, drops to 0, and then we stop there, okay? Because we know that afterwards it's going to be only noise. Okay. I think there is a Matlab function also for the computation of tau directly, but I wanted to show you all the steps. Okay? So we can do two things, okay? One of them is like maybe we sum up everything, okay? Another one is to simply drop all those guys out, okay? And then work only with this part here, okay? Only with the second half since this function computed the covariance forward and also backwards, okay? And of course, this is symmetric. This is symmetric. Okay. Okay. Okay, so, with this estimate for the autocorrelation time, we then can compute the number of effective samples in the Markov chain. Okay? And with this effective number of samples in the Markov chain, we can then compute the variance of the mean value. Okay? This is not the variance of the chain. Okay? This is the variance of the chain, and this is the variance of the mean. Okay? And why this is so important? Because you can show that actually, from the central limit theorem, okay? From the central limit theorem, we can show that the mean, it has a Gaussian distribution, okay? So the mean is Gaussian. The mean that you obtain with the Markov chain, it's Gaussian, okay? So since this is Gaussian, okay? Since this is Gaussian, I mean, this would be like a standard Gaussian, where here we have the mean of the samples. Here we have the variance of the mean, and the variance of the mean is the variance of the samples divided by the number of effective samples. And this is the variance of all samples in the Markov chain. Okay? All samples in the Markov chain. So we can represent the mean in terms of a confidence interval with any confidence level that we would like, because this is actually Gaussian, okay? So we can present the means. We can present the means with something like this, okay? We can present the mean and its associated confidence interval, okay? So if this is like for a 99% confidence intervals, this constant here is 2.576. Okay. Okay. And also we saw that. Okay. Any questions about this? Okay. So another point is that how do we know that the chain has converged? We saw different ways of looking at it, okay? You always have to look at the chains, and we can look at the log of the posterior, but also we can compute the means after we drop out the samples during the burning period, okay? We can compute the mean at the beginning of the Markov chain and the mean at the end of the Markov chain, okay? And this is was proposed by Gilwick. And so we compute this mean with the first 10% of the samples, and the mean with the last 50% of the samples, and we expect that they should be very close. Okay? So this would be a representation that this is actually, the chain has actually converged. Okay? And this is one of the papers that I mentioned to you that works with multiple chains. Okay? This paper by Gelman and Rubin. Okay, so now another example. What I propose is that this is 3:30. Maybe we saw this example. We make a short break, okay, and then we come out for the last part of the presentation. Okay. So this example, it's still a semi-infinite medium, initially at this temperature T0, and we have an excitation. We have an imposed heat flux at the surface x equals 0, which is Q0 multiplied by some function of time, okay? Okay. And this is the mathematical formulation of the problem. Let's write it in dimensionless form, okay? And these are reference values for thermal conductivity, volumetric heat capacity, etc. And then we get this representation which has two parameters, okay? Two parameters, alpha star and K star, so it's a dimensionless thermal diffusivity and a dimensionless thermal conductivity. Okay? If this function that represents the heat flux is constant, this is our solution at x equals 0, okay? At the surface. So this is the solution at the surface where this quantity here, it's square root of K star C star. This is also, it's the square root of the multiplication of two thermophysical properties. So this is also a thermophysical property, which is called effusivity. Okay? This is called effusivity. So since this is E star, we see that the heat flux phi, okay, and the thermal diffusivity, they are perfectly correlated. Okay? They are perfectly correlated. Phi and E. Okay? So we have two parameters. So the idea here is, okay, let's take measurements at the surface, and I want to estimate any of these two parameters. I know that I cannot estimate both parameters, right? I cannot estimate both parameters because they are perfectly correlated. Okay? In practical terms, this is what is called a hot disk. And it's usually used for estimating this, for measuring this thermal effusivity of the material. Okay? However, we need to know phi, right? But we cannot know phi and E at the same time. From the same experiment. Okay? So one possibility is, for example, let's say that we use some reference material, okay? And with some reference material, we estimate phi. And from this phi that is estimated with this reference material, we then use it for the characterization of other materials. Okay? Characterization of other materials that we would be interested in measuring this thermal effusivity. Okay? But by only taking measurements at the surface, we know that it's impossible to characterize, to obtain both the thermal effusivity and the heat flux. Okay? But from the Bayesian point of view, my solution has two parameters, and I need to provide priors for both parameters. Okay? Obviously, when we are characterizing the experimental setup and we use the reference material, I'm going to provide a very informative prior for the effusivity, so that I get an estimate for the heat flux. So I need to provide a prior for the effusivity, which I know the mean very well, and with a small standard deviation, with a small variance. And afterwards, we get this mean value and this variance for the, or any other statistics for, for the heat flux, and then we can characterize all the materials. Okay? But we cannot do both at the same time. Okay? All right. So let's take this plate, hot plate. Okay. Okay. So everything here is dimensionless, so I'm assuming that all values are 1. Okay. So all the exact values are 1. So the value of E is 1, the heat flux is 1. Okay. And this is like the final time, and this is an analytical solution, and this is the sensitivity coefficients with respect to the heat flux and also with respect to E. Okay? And this is the a numerical integration of the solution. Okay? Instead of using that analytical solution, I'm doing a numerical integration. And let's stop here. Oops, sorry. And only to check the sensitivity coefficients. Okay. So there they are, okay? First, the analytical and the numerical solution, they are all below here, the sensitivity coefficient of the heat flux. But see, the two sensitivity coefficients, they are perfectly proportional, okay, as we expected, okay? One is positive and another is negative because one parameter is in the numerator and the other one is in the denominator, but they are perfectly correlated. Okay, breakpoints. Where do I get out of this? Okay, quit debugging here. Okay. Okay. Now I'm going to generate measurements with this 1% of, with a standard deviation which is 1% of the maximum temperature. Okay, so this will be the exact and dimensionless temperatures, and let's start the Markov chain Metropolis-Hastings algorithm. I'm considering here 50,000 states and 10,000 states for the burning period. Okay, and I'm starting. I have two parameters, and this is the relative standard deviation of a Gaussian proposal. So I'm using Gaussian proposals for both parameters. And what else? Okay, the priors. Okay, the priors. Let's assume that these are the means. I'm using here truncated Gaussians, truncated Gaussian priors again. Okay, where I'm assuming that the mean of this prior is the exact flux and the exact effusivity, okay? And I'm assuming that the effusivity has a standard deviation of 1% of this value, okay? And the flux has 10% of this value. So I'm kind of calibrating the sensor, okay? Okay, I'm calibrating the sensor. Actually, I can calibrate this. Let's say I can put this here 1.5. Doesn't matter. Okay. Okay. Sorry. Times. Okay. And so these are the only to compute here the prior. Okay. So I'm writing the prior already in a more in the same form that we wrote in the transparencies, okay? Again, I'm only computing the exponents, whatever is inside the exponents, okay? And so I have the prior, I have the likelihood because I have the estimates of the temperature at the first state of the Markov chain. And I go for the Metropolis Hastings as we have seen before, you know, Gaussian Proposal. And so I compute the new posterior, okay? I check if the parameters are negative, because I know that both parameters, they have to be positive, okay? So if they are negative, I do not accept the candidates, and I don't have to do all the tests, because their probability is 0, okay? So I move directly to that last steps in the Metropolis Hastings algorithm, okay? So I compute a new priori, the priori for the candidates. I compute the likelihood for the candidates and the posterior, and I do exactly as before, okay? Okay. So this is the Metropolis Hastings. This is the Metropolis Hastings, exactly as before. So after, when I do the statistics here, okay, I get from all parameters that were saved here, I remove those that correspond to the burning state, okay? And then I compute their mean and standard deviation. I compute the mean at the beginning of the Markov chain, at the end of the Markov chain to compare them. Okay? So this is like the mean in the beginning and the mean at the end of the Markov chain. Their difference to compare. And then I compute the normalized autocovariance function with that Matlab function that I have shown you before. But then I drop off here, you see, I remove from this vector the first half, because you remember that it's not centered. It's centered at the number of samples, because it computes forward and backwards the covariance. And then I also compute the cross correlation between the two chains. Okay, I compute the cross correlation, and this is a figure of these two of the autocovariance function for for each chain, and also the cross correlation function. And I compute the autocorrelation time. And when ρ is less than 0, okay, then this will be my cutting point, the limit of my summation to compute tau. Okay. And then I can compute, you see here, the variance of the mean is the integrated autocorrelation time multiplied by the variance of the samples and divided by the number of samples. Okay. And this is like the histograms and all that for the Markov chains. Okay. So in this case, I'm calibrating the sensor. Okay, I'm calibrating the sensor. So I have a very informative prior for the effusivity, and a prior with a large variance for the heat flux. Okay, So this is the log of the posterior. Okay. So we see that we get good convergence of the chain. This is the number of accepted states. All right? So we have about 14,000 for 50,000. So this is a good number. Okay, so it's more or less 30%. This is effusivity, okay? So we have a nice Gaussian distribution because we had a nice prior, right? We have a very nice prior. And what about the heat flux? This is what we get for the heat flux, okay? So we get a very nice estimate for the heat flux, although the two parameters are correlated, they are completely correlated, because we kind of fixed one of the parameters, but we do not fix it deterministically as we do for the classical parameter estimation, okay? We have fixed it with an informative prior. So when we estimate the heat flux, we are actually taking into account all the uncertainties that are considered in the effusivity, okay? In the effusivity of the reference material that's being used for calibrating our instrument, our sensor, okay? All right, so this is a picture of all the states. You see this is the burning period, and this is the region that we are interested in, okay? And what's nice to see is that, you see, this is almost like a line. This is almost like a line, no? Why? Because the parameters, they are perfectly correlated. Do you remember, like when I have drawn on the blackboard, it's like if we had an objective function that would not have one single minimum, but a real value, no? Because the parameters, they are totally correlated. Okay? And these are the Markov chains for the effusivity. See, they look nice. The Markov chains for the heat flux. These are the estimated means. I mean, they are relative means, so they are they are 1. So both of them, you see, this is the 99 confidence interval for the means. So this was obtained with the integrated autocorrelation time. And this is the normalized autocovariance functions for both the flux, the effusivity, and also the cross-correlation between the two chains. You see, they are identical. And why they are identical? Because the parameters, they are perfectly correlated, okay? They're perfectly correlated. And you can see that, you see, this drops to 0 with about like 300, 400 states, no? So this means that almost, I don't have the exact number here for the integrated autocorrelation time, but you need a lot of states to have an independent sample, no? Because this is taking a long time to drop to 0. Okay? This is the analysis of the convergence. This is the difference between the means at the beginning and at the end of the Markov chain. You see that this is very small, and which is kind of represented here too, okay? So this is the mean at the beginning and the mean at the end of the Markov chain. So we have all the references now to decide if this is a good chain or not. No? We need to look at the integrated autocorrelation time. We need to see the confidence intervals of the means. We need to see if the posterior is converged. We need to see if the chains look nice. And we also look at the means, the difference between the means in the beginning and the end of the chain. Okay. All right. So now let's do the let's do something different here, okay? Let's consider that we know the flux very well, okay? Let's consider that we know the flux very well. And we don't know the effusivity, okay? We may even say here that we have maybe 3 times the exact value of the effusivity, okay? So we already calibrated the sensor, and now we are measuring the effusivity of a different material, okay? So we are given a very informative prior for the flux, but a very lousy prior for the effusivity, okay? I'm not even saying that the effusivity is like at some range. I'm only saying, that this is positive, okay? I'm saying that this is positive. Okay. Okay, so this is the posterior. These are the accepted states, 30%. And there we have our effusivity, okay? So although this is not exactly 1, okay? This is very close to 1, small standard deviation. And here we have the heat flux, okay? Here we have the heat flux. And now take a look at the samples of the Markov chain. You see, this is they are very correlated. It's basically a line, you know. It's a line because of the correlation of the parameters. This is the chain for the effusivity, the chain for the heat flux, the estimated means, which look nice. Again, the normalized autocovariance functions, and also the cross correlation, which they are identical because all the parameters, they are fully correlated. The relative difference between the means and the means at the beginning and at the end of the Markov chain, which is very nice, okay? So now, instead of fixing the effusivity, we have fixed the flux, okay? Now let's take a look at if we had not seen the sensitivity coefficients, if we had not realized that the parameters are correlated, okay? So what I mean is that, okay, I want to estimate both parameters, right? I want to estimate both parameters. My advisor told me to estimate both parameters. I have this code, I have this supernatural Markov chain Monte Carlo method, and I give priors, I have prior information, I have likelihood, and I know how to estimate both parameters, okay? So the mean flux, let's say this is oops, I'm sorry. Here, okay, this is 1.5, okay, and this is 10%. No, I don't care. I don't have to do calibration. I don't have to do the calibration of the sensor, okay? No worries. Give me the sample, and I'll get a diffusivity value for you, okay? So, I'm sorry. Let's see what we get. Nothing, right? We cannot get enough. Just 1 second, please. Okay, our posterior, wow, Very nice posterior, right? It converged somewhere. Accepted states. Not bad, okay? Effusivity. Centered about like 2.25. And let me put here side by side the histogram for the heat flux. Centered also around 2.25. And if you take a look at those two histograms, they're exactly the same. They're exactly the same because the chains, they're completely correlated, right? They're completely correlated. Our joint posterior distribution, you see our line here demonstrated the total correlation of the two parameters. And now let's try to put the two chains together, okay? So this is the chain for the effusivity, and this is the chain for the heat flux. Take a look and see how they look alike. See? This point here, this point here, this point here, this point here, see? Here and here, there, okay? Because of the total correlation between the two parameters. Okay? And there, so they look like convergent, right? They look like equilibrium distributions for these two parameters, but they're meaningless because they're completely correlated. And this is revealed here. Now, that's what we get when we examine the autocovariance function, okay? Very bad autocovariance function, okay? Depending on the initial gas and the initial state and also the mean that we provide for this prior, no? You may get something like drops to 0 in 10,000 states, which is very bad. Okay? So we, despite that, that we have a very good method that we can take into account all the prior information that we have for the parameters in a statistical sense, and besides get 1 point estimate for the solution of the inverse problem, we can actually compute all the statistics from those samples that are associated with our posterior distribution, okay? That's hopefully represent our posterior distribution. You have to still be very careful with the correlation of the parameters. You have to be careful with the number of samples that you use in the Markov chains, the proposal, and the priors. Okay? The priors should actually reflect your knowledge about the parameters before you make the new experiments. Okay? So that's the main message that you need to take. Okay? So don't think that you don't need to examine the sensitivity coefficients before estimating the parameters, because you do need them. Okay? You do need to estimate your sensitivity coefficients. Okay? And you may get something, as we have seen. Okay? You get something, but this can be completely meaningless. Okay? This can be completely meaningless. So, questions? Oh, this is 10 to 4. Maybe we go ahead a little bit and we stop earlier, okay? Is that okay? Okay, so the last part of the talk is about accelerating the solution with the Markov chain Monte Carlo method. Okay? We have developed in the past some techniques for some special cases, for example, like Enrique has shown this morning. Also, the work that Carolina and Luis did here. where we have integral transformed the measurements obtained, for example, with an infrared camera. And so that we could kind of compress the data, or in the case of Henrique, instead of working with a nonlinear estimation problem, work with a linear estimation problem. Okay. So there are techniques that work very, very well for some specific cases. And these two techniques that I would like to show you are techniques, and there are others. I'm only showing you here two techniques that they can be applied for any case. Okay, so you're actually working with reduced models. The idea is to replace your complete model by some reduced model, so that you can compute the likelihood and compute the generate your Markov chain very fast. Okay, so one example is this plate. Okay, it's one plate, very thin plate. Okay, it's size A, B, C. Okay, the thickness of the plate is C, very thin plate. And heat conduction problem, and we have an imposed heat flux here at the top boundary. Okay, so this is the solution of the three-dimensional problem, where we have this is the temperature at the top surface and at the bottom surface. Okay, in the case that the heat flux is concentrated at 2 points here, like 2 lasers, and here is like concentrated at one big region at the center. Okay, like a big laser there. Okay, so very large heat flux concentrated in these regions. Okay, and we can see that we have very large temperature gradients, not only over the surface of the plate, in the x and y directions, but also across the plate. Okay, because since this is a very thin plate and it's a metal, I think this is 2 or 3 millimeter plate, and it's like a steel, it's like a carbon steel, and so we are tempted to use a lumped formulation in the z direction. Okay? So what I'm showing you is that see from the top to the bottom surface, see there are almost 300 Kelvin temperature difference. Okay? So this means that we cannot directly apply a lumped model. Okay? And so we have a complete three-dimensional model. The gradients are very large, so that we have to take into account the temperature dependence of thermal conductivity and volumetric heat capacity. Okay, so this is a three-dimensional problem, three-dimensional nonlinear, and although it's only a heat conduction and diffusion problem, you can imagine that to generate samples for the Markov chain by solving this problem may take forever. Okay? And then one idea, okay, I want to use a reduced model, which I linearize. Okay, I linearize by computing the properties at some temperature T star. And instead of working with this three-dimensional problem, after I linearize, I integrate here in Z. Okay, I integrate in Z, and I work with the mean temperature in the Z direction, instead of working with the actual temperature, the three-dimensional temperature. Okay. So this is already one level of approximation, because the nonlinear problem, we have linearized it, okay, and computing the properties at some specific temperature. Okay. Okay, from the classical lumped formulation, the temperatures we completely neglect the gradients, so the temperatures at both surfaces is equal to the mean temperature. Okay. And while we can have this improved lumped formulation, which was developed by Renato Cotta and Mihail Mihailovich in their book, okay, where we do not fully neglect the gradients, but we take into account the gradients in an approximate form. Okay, so and then the temperatures at the surface, they are related to the mean temperatures by these expressions, which it's kind of post-processing. This is only post-processing, okay? So I solve this problem for the mean temperature. If I consider lumped formulation, classical lumped, the mean temperature is equal to the surface temperatures. Sorry, the surface temperature is equal to the mean temperature. In this case, the surface temperatures are computed by these expressions, also by only post-processing, okay? And the complete model takes 7.2 seconds, and this reduced model takes less than 0.1 second. So it's much faster, okay? But when we look at the error between the solution of the complete model and the reduced model, let's say for a case that we have these two heat sources here, for the classical lumped model, you see we have errors about 250 Kelvin. And for the improved lumped, the errors are much smaller. They're around 40 Kelvin. But we might not live with this 40 Kelvin error, okay? This might be too much, okay? This might be too much. But of course, for the solution of the inverse problem, it is of great interest to replace this complete model, okay? This complete model by this reduced model, let's say with this improved lumped formulation, okay? So the idea here is that by taking measurements, okay, we want to estimate the heat flux at this top surface by taking measurements at the bottom surface, okay? And these are local measurements, so these are taken with kind of an infrared camera. Okay, so one technique that this has been developed by Christian and Fox, it's called the delayed acceptance Metropolis-Hastings algorithm. It's very simple. It's very simple. You use your reduced model to generate candidates that can be accepted, okay? And remember that usually you should have an acceptance ratio of around 30%, okay? So why generate candidates with the complete model if only 30% of them shall be accepted, okay? That's the basic idea, okay? So you generate candidates, good candidates, with your reduced model, and when the candidates are accepted with the reduced model, you run the complete model maybe accept them, okay? You still need to verify if these candidates would be good candidates for the complete model. So you actually have two loops, okay? Two Metropolis-Hastings loops, okay? So you have one loop with the reduced model, and the posterior here is computed with the reduced model. And if this candidate is accepted, okay? If it's not accepted, we continue here, okay? Generating samples, okay? And if this is accepted, we move to our next step with the complete model, okay? And then compute the posterior with the complete model. And then we decide if we accept it or not, okay? If we should accept it or not. So it's very simple. And the implementation is very simple too, okay? Okay, so an example with the prior distribution given in terms of a total variation, as we have seen on Monday, okay? Why a total variation? Because we expect, from the physics of the problem, we expect that this heat flux is kind of concentrated at some points, okay? And we would like to still get an estimate that maintains the gradients, okay? That does not completely smooth out the solution, like in the Gaussian Markov random field. So that's why I'm using a total variation prior. And this is what we get, okay? This is what we get with the total variation prior and the delayed acceptance Metropolis-Hastings. Okay? So notice that the prior, it does not give any quantitative information and even any qualitative information about where the heat flux is located. Okay? We only consider a prior that we would like to maintain the gradients. Okay? So two different cases, we get good estimates of the location, also of the magnitudes. Okay? Although we see some oscillations in this region where the heat flux is located because the problem is very opposed. Okay? Very opposed. Okay, and another technique was developed by Jari Kaipio, and this is in his book, Kaipio and Sommersalo, so developed this is in his book and several other papers. And this is called approximation error model. Okay? So remember that our measurement model, okay, was based on the complete model for our physical problem, okay? On a very accurate model, mathematical model that supposedly perfectly represents the physics of our problem, okay? So this is our measurement model, okay? So which was additive, and in some sense we assumed that this was also Gaussian with zero mean and a non-covariance matrix W. Okay, non-covariance matrix W. Okay, but we don't want to work with this complete model because the computation of the likelihood would be too expensive. Okay? So we want to work with a simpler, reduced model. Okay? So instead of, I'm going to add and subtract here the reduced model, T. Okay? And when we do this, we notice that it appears here the error between the complete model and the reduced model. Okay? So we are tempted to, and we can do this, no? We can add this error to the experimental errors and represent them in terms of an experimental and modeling error. Okay? So while before we had only the experimental error, when we replace the complete model by the reduced model, now it appears this error eta, which is the sum of the experimental error and the modeling error. Okay? The question is how we compute this modeling error, because we have a model, we have a statistical model for the experimental error, which in our case was given by this Gaussian distribution, okay? But how do we model epsilon, okay? How do we model epsilon? And although this error might look deterministic, it's not. It's not because the error depends on the parameters, and the parameters are stochastic. They are random. The parameters are random, okay? So the idea is very simple. The idea is very simple. Is to model eta, okay? To compute statistics for epsilon, okay? How? We take samples from the parameters. We do Monte Carlo. We do Monte Carlo by taking samples for the parameters. Okay? And then we compute samples for epsilon, and then we represent epsilon in terms of some statistical distribution. Okay? And this can be done offline, but of course, in order to do this, we need an informative prior. We cannot work with the total variation prior because the total variation prior has an unlimited variance. We need some prior with, we need a prior with some limited variance. And so this can be done offline, okay? And what Kaipio and Sommersalo proposed is that this error eta, epsilon actually, be represented in terms of a Gaussian distribution, okay? With a Gaussian distribution so that the error the mean of eta is going to be given by the mean of epsilon, since the mean of E here is 0. Okay? And the covariance matrix of eta is given by the covariance matrix of epsilon, which is the modeling error, plus the covariance matrix of the measurements, which is W. Okay? This is already a big simplification because epsilon depends on the parameters, depends on the priors. Okay? And we are neglecting this linear dependence between eta and the parameters, because we compute epsilon based on the priors. Okay? Based on the priors. And although this is a big simplification, it works very well. Okay? It works very well. And of course, there is a complete error model where this linear dependence is taken into account, and these are not representing them here. Okay? So in this case, when we worked with the approximation error model, I have already shown this on Monday. We have worked with okay, so now we have a modified likelihood, okay? We have a modified likelihood because our model for the error is not only for the experimental error, okay? So we have to modify the likelihood and the covariance matrix, the covariance matrix, which was W for the likelihood, now is W tilde, okay? And the mean, which was 0, now it's given by the mean of the modeling error. Okay? Okay. And in this case, we have applied a Gaussian prior for which this coefficient gamma, this is a representation of our lack of knowledge about the covariance matrix gamma for the prior. So we have we compute it as a hyperparameter with this hyperprior given in terms of a Rayleigh distribution, and this we have discussed also at the end of last class. Okay? And in order to generate this Gaussian prior, we have used a very lousy lumped model. Okay? So we kind of, with some experiments, we generated this prior with this loss lumped model, and then we computed the solutions with other measurements. Okay? And so let me show you directly what we get here. You see, these are the Gaussian prior plus the approximation error model. We get this very nice solution. Okay? And this is much faster than actually we could have with the complete model, because the complete model takes more than 7 seconds and this one takes 0.1 second. But of course, we had to do that we have to do this offline Monte Carlo to compute the statistics of the approximation error. Okay, and this is for a larger error. We still get a very large error, actually. So we get something nice, although we have some oscillations here because of the opposed character of the problem. And this is the figure that I wanted to show you. These are the residuals. This would be the residuals if we had only replaced the complete model by the simplified model. Okay? We would get these residuals, where we have here of the order of 40K, as we have seen before. And when we do the Gaussian prior with the approximation error model, we still see that our larger residuals are in this region around where the heat flux was applied, okay? But they have decreased to something around 15 Kelvin. And before they were like 40 Kelvin. Okay. So, and we have been doing this for many cases, and we have been getting very nice results, okay? Another application in this case, it's called a line heat source. it's one probe. It's like a needle that is heated inside a fluid, okay? And when we heat this needle, the objective is to take temperatures inside, to take temperature measurements inside the needle to recover the properties of the fluid. And usually people use this with a heat conduction model, a purely heat conduction model. But when you have a fluid, you see that you can have like, this is the dimensionless temperatures, okay? The dimensionless velocities, okay? So you have the currents that are imposed by the natural convection around this needle that is heated, okay? So actually, this should be taken into account, otherwise you estimate a thermal conductivity which is larger than the actual value, okay? In other words, if we had only the conduction model, we would have this black line here, while if we consider the natural convection model, the temperature at the center of the probe would be this red line, okay? So the effect is like if we were increasing the thermal conductivity, okay? So when we do this, the approximation error model, you see, this is what we get, okay? We actually can track very well the temperatures that were obtained with the natural convection probe. Okay, I guess this is it. Questions?
What happens if you do not use the mean for the error model? But if you use the whole distribution, what happens? Yeah.
If I don't use this?
No, if you don't, the first line, if you don't use the mean for the error, use the distribution.
No, I'm using a distribution. But I'm representing this guy here in terms of a Gaussian distribution. I'm representing the, you have to do your offline Monte Carlo, okay? So you start taking samples. Start taking samples from the parameters, and then you compute the reduced model and the complete model. You compute a sample for epsilon. And then you do this for many samples. And you have to look, to decide how many samples you need, you have to look at this mean, at the mean, and also the covariance matrix of epsilon. Okay? Because the convergence of the mean is very fast, but the convergence of the covariance matrix is much slower. Slower. And, but the question is, okay, I have all those samples, and how do I represent them statistically? Okay? So their idea was to represent them in terms of a Gaussian distribution. Okay? Which is nice because many times you have a Gaussian prior. And when you have a Gaussian prior, you're simply modifying you don't have to modify your code. No? You only have to modify your likelihood by considering the mean of the modeling error and the covariance matrix, which is now given by the covariance, approximately given by the covariance matrix of your measurements plus the covariance error or the covariance matrix of your modeling errors. Okay, so you're actually considering you're not only considering the mean, you know, you're considering that the error is Gaussian, and that's why you also modify the covariance matrix. This is approximate, no? It's approximate. Even by approximating your modeling errors in terms of this Gaussian distribution, the mean has other terms here which have to do with the linear dependence of epsilon with respect to the parameters, because you're sampling from the parameters to compute epsilon, so they are not completely independent. No? And also there is an additional term here for the covariance matrix. But And that's why they call this enhanced error model. But there is a complete error model. The complete error model takes into account this other stuff in here. Okay, and we have never, we compared the complete and the enhanced error model for one single problem, which was this one here. This one. Same thing, same stuff. And so we, in general, we have been only applying the enhanced error model. So you actually have to do this offline in Monte Carlo, which takes time, because you might need to like thousands of times the complete model. But you never do this for one single case, for one single inversion. You do this when you will need to solve the inverse problem many times, and sometimes you need like of the order of million states, millions of states in the Markov chains for the solution of the inverse problem. There are some techniques, we played with this a little bit this year, that when you do this, and you compute the reduced model, the complete model, reduced model, complete model, and you generate the approximation error model sequentially. Okay? Cesar did this for his master thesis when he applied the Kalman filter for this problem. So he was kind of applying computing the reduced model and the complete model as he advanced on the solution of the inverse problem. Up to one point that you basically only need to run the reduced model. You don't need the complete model. So this is something that Colin Fox did with one of his students too, and it's a very interesting approach, and it worked very nice for Cesar when we are applying for other work. We still don't have like what to do exactly, but these two things are very general. Okay. Okay, so thank you very much for coming, for staying until now. Thank you. Thank you. Thank you. Good.